Hi, this is Professor Sartor, and I'm going to be working through the first 10 questions on Practice Test 2, which covers Chapter 3 and 4. Our first question says, evaluate the following function at the values -4, 8, and a, with our function f of t being t over t plus 1. So we'll start off by evaluating the function at the first value of -4, which means that we're finding f of -4. Now, to evaluate a function at a specific value, we want to substitute that value in for the variable. So everywhere we see a t, we want to change that to -4. So f of -4 would be -4 over -4 plus 1. And now we've evaluated the function and we want to simplify the expression using order of operations. And we'll simplify the denominator first. -4 plus 1 is -3. And with every fraction you want to simplify or write it in lowest terms. So a negative divided by a negative is a positive, so that becomes 4/3. Let's give the next one a try. We want to evaluate the function f at t equals 8. Everywhere we see a t, we want to change it to 8. So we would have 8 over 8 plus 1. We're going to simplify. 8 plus 1 is 9. And 8/9 is in lowest terms. So f of 8 is 8/9. The last value here is a variable instead of a number, but the process is the same. Everywhere we see a t, we want to change it to a. That would give us a over a plus 1. And since a and 1 are not like terms, we can't simplify that. So we're going to leave our expression as a over a plus 1. Our next problem gives a graph and says, for what value of x is g of x equals 6? Our graph, this blue line here, represents the function g of x. And once again, the question says, for what value of x is g of x equals 6? Now, for this example, we have to keep in mind that the notation g of x means the same thing as y. So this is telling us that y equals 6. And the question is asking us for an x value. For what value of x? So we're going to take a look at our graph, and we're going to be looking for when y equals 6. So we've got our y scale here. That's the vertical scale. And we're looking for when y equals 6. So here I have y equals 6 on the vertical scale. And I want to go all the way over to the graph, and I notice that right here I have a spot on the graph where the y coordinate is 6. So let me mark that down. The y is 6. And if I look down on the x scale from that point, I can find out what the x value is at that point. And that is -5. So what I can now say is that f of -5 is equal to 6. I'm sorry, that would be g. G of -5 is 6. And so our answer to the question is that at an x value of -5, g of x is equal to 6. The next example says, determine whether the relation represents a function. State the domain and range of the relation. So the relation is this picture right here. It's showing us a relationship between these names and these dates. So what we need to know is the definition of a function. So for a definition of a function is a relation in which every first coordinate corresponds to exactly one second coordinate. So when we say corresponds, these arrows represents the correspondence between the two sets. So Sandy corresponds with January 15th, Emily corresponds with January 26th, Marie corresponds with January 26th, John corresponds with February 27th, and Micah with October 2nd. So a relation is when we have a correspondence, but a function is when we have a special type of relation in which every first coordinate corresponds to exactly one second coordinate. So we want to focus on the first coordinates and see how many correspondences they have. Sandy corresponds just once with January 15th. Emily responds just once with January 26th. Marie just once with January 26th. And John just once with February 27th. And Micah just once with October 2nd. So that does satisfy the definition of a function in which each first coordinate corresponds to exactly one second coordinate. So we're going to say that yes, this relation represents a function. Then the next part of this says to state the domain. The domain is a list of all the first coordinates, and the range is a list of all the second coordinates. So the domain is going to be Sandy, Emily, Marie, John, and Micah. And the range is all the second coordinates, and that's going to be January 15th, 26th, February 27th, and October 2nd. So the range is a list of all those dates. Our next question says, determine whether the following equation represents y as a function of x. So does this equation 3x minus 8y equals 24 represent y as a function of x? So the first thing that we want to do to make that decision is to rewrite our equation in y equals form. So we're going to write 3x minus 8y equals 24. We want to rewrite it so that we have y by itself on one side. So we're going to subtract 3x on both sides. It gives me negative 8y equals negative 3x plus 24. We're going to divide both sides by negative 8. And that gives me y equals a positive 3/8 x minus 3. So first I've rewritten the equation in y equals form. That's writing it as y as a function of x. And then we want to decide whether this equation represents a function. So we have to remember the definition of a function. Every first coordinate corresponds to exactly one second coordinate. So our first coordinates are our x's and our second coordinates are our y's. So for every x, we need to have exactly one y. And we will see that if we choose a value of x, say choose a value of x like x equals 0, we'll find that y equals 3/8 times 0 minus 3. And then that simplifies to be negative 3. So we chose a value of x, we have a first coordinate, and it's corresponding to exactly 1 second coordinate. Now we did one example, but it really has to be true for every first coordinate. So if we choose a different value of x, will that also correspond to exactly 1 second coordinate? So I chose a second x value of 8. If we substitute that in, we would get the 8's canceling out to be 3. 3 minus 3 is 0. And we get, once again, 1 second coordinate. So no matter what value of x we choose, we're going to substitute into this equation and just get one value of y. So this is a function. The next question says, use the vertical line test to determine whether the graph represents a function. So is the graph a function? So once again, we're trying to decide whether this is a function, this picture this time, and it goes back to that definition of a function again. Every x has exactly one y. And the way we do that with graphs is a vertical line test. So either you're going to physically do this or just in your head, but you want to imagine drawing vertical lines on every part of the graph, and you're going to pay attention to how many times those vertical lines cross the graph. So you notice here that I have a couple places where if I draw a vertical line, it crosses the graph in 3 places. So what that means is that I've got an x value, so for example in this spot here, I've got an x value of 2, but y values of -4, -2, and 3. So you've got one x value corresponding to multiple y values, which violates the definition of a function. A function should have every x having exactly one y. So for this example, it's not a function because the vertical lines cross the graph in more than one place. In other examples that might be functions, if it only crosses the graph in one place, then it is a function. So for this example, it is not a function. The next question says, classify the given function as a polynomial function, a rational function, or a root function. Then find the domain. Write the domain in interval notation. So our function is f of x equals 4x cubed minus 3x. So we want to decide whether this function is a root function, a rational function, or a polynomial function. So let's go through each category just briefly. A root function, or sometimes called a radical function, will have a radical in the equation. So it'll have like a square root or a cube root. A rational function is a function where you would have a fraction, and that fraction would have a variable in the denominator. And then finally, a polynomial function. Polynomial functions don't have radicals or fractions. Well, they might have a fraction in the coefficient, but you wouldn't have a variable in the denominator. And the powers on the variables are going to be whole number powers. So for this example, looking at it, I don't see any radicals and I don't see any fractions. So I'm looking at the powers on x, and I've got a power of 3 on this one and a power of 1 on this one, and those are both whole numbers. So I would classify this as a polynomial. And then once we decide that it's a polynomial function, we want to answer the second part, which is what is the domain of this function? So all polynomials will have a domain of all real numbers. So we don't really need to do any calculation on this one. It's more of a memorization thing. Once you know you have a polynomial function, you know that any value of x can be substituted in, and we write that the domain is from -infinity to infinity. That is saying that all values of x can be substituted into this function from -infinity to infinity. The next example says classify the given function as polynomial, rational, or root, and then find the domain. Write the domain in interval notation. So this is the same directions as the last example. And this time we have h of x equals x squared plus 8 over x squared minus 3x minus 4. So first we want to classify it. We've got our three types: root, polynomial, and rational. So root function, those are going to have radicals in them. Square roots, cube roots, and so forth. Polynomial function, these are the ones with no fractions, no radicals. You're going to have just variables to whole number powers. And then you have the last category, rational functions. Those are going to have variables in the denominator. So you can see that this example does have variables in the denominator. So I'm going to categorize this as a rational function. And then we want to find the domain of this rational function. So with rational functions, because they have variables in the denominator, we're concerned with the denominator equaling 0. If you have the denominator of a fraction equaling 0, this is something that is undefined. So our strategy for finding the domain is to set the denominator equal to 0. So we're going to take that denominator of x squared minus 3x minus 4. We're going to set that equal to 0. So we're trying to find when the denominator is equal to 0, so we can find out where the function is undefined. So this is a quadratic equation, which I can solve by factoring. We factor. The numbers that go here and here need to multiply to be x squared, so that's going to be x and x. The numbers that go here and here need to multiply to be -4. So we have a couple choices. Factors of 4 are 1 and 4 and 2 and 2. But I'm going to use 1 and 4 because that's going to help me get that middle number of 3. So if I use a -4 and a +1, that's going to give me the right factorization. If you're not so confident on factoring, make sure you check to make sure that you factored it right. So if I multiply this factorization out on the side, that would give me x squared minus 4x plus x minus 4. And if I combine like terms in the middle, I can see that I've chosen the correct factorization. Once you've got it factored, then you're going to set each factor equal to 0. That's using the zero product property. And if I subtract 1 on both sides, I'm going to get x equals -1. Add 4 on both sides, I get x equals 4. So these two values are going to cause the denominator to equal 0. So they have to be excluded from the domain. So what I'm doing is I'm going to start off with assuming that the domain is all real numbers or -infinity to infinity. But I figured out these values that I need to exclude. So I'm going to exclude -1 and I'm going to exclude 4. So let me write that out here. I'm putting an open circle to say that I'm not counting those values, but we are going to include all of the other values that are on the number line. Drawing this picture is going to help me write the interval notation. So I'm going to write each interval in interval notation. So this first one here starts at negative infinity and goes to -1. You'll notice I've used parentheses next to the infinity. Infinity always gets parentheses next to it. And next to the -1, we use those parentheses to indicate that -1 is not part of the set. We use brackets when something is part of the set. So then I write the next interval. The next interval goes from -1 to 4. -1 is the lower bound, 4 is the upper bound. We're going to use parentheses on both of those because they're not part of the set. And then from 4 to infinity is the last interval. So that gives us our interval notation, and that is the domain of our function h of x. So our next example has the same directions. Classify the given function as a polynomial, rational, or root function, and then find the domain. Write the domain in interval notation. So on this example, we have the function g of x equals the 8th root of 7 minus x. So our three categories, once again, are root, that's when we have radicals, polynomial, no radicals or fractions, rational, that's when we have variables in the denominator with fractions. So this one very clearly has a radical in it. But we have to be careful. Well, it is a root function, but once we're finding the domain, we have to be careful because there's actually two categories of these root functions. The two categories are the even roots and the odd roots. And what we're talking about is the index on that root. So I'm going to highlight the index on that root, and this one has an 8. So because 8 is even, we have an even root. So what we're worried about with the even roots is negative numbers. If we, for example, take the square root of -1, we get I, the imaginary unit, and that is not a real number. So when finding the domain, we want to make sure that what's underneath the radical is either positive or 0, not negative, to make sure we avoid those imaginary numbers. So we're going to take what's underneath the radical, and we want to make that greater than or equal to 0. Greater than 0 is positive, and then equal to 0 is 0. So you can see we're avoiding less than 0. Less than 0 would be negative. And we're going to solve this inequality. Subtract 7 on both sides. And to get x by itself, I would divide by -1. And when I divide an inequality by a negative, I need to reverse the inequality symbol. So it changes from a greater than or equal to a less than or equal to. So that gives me x is less than or equal to 7. If I were to put that on the number line, I would mark out that 7 and put a filled in dot on the 7, and I would shade to the left of 7 because that's less than 7. And then I can write the interval notation. So the lower bound for this shaded region would be -infinity. I'm using a parenthesis on infinity. And that would go all the way up to 7, and I would use a bracket on the 7 because 7 is part of the domain. So the domain for this example would be -infinity to 7 with a bracket. Now, before we move on from this example, I just want to mention that the other category of roots, the odd roots, we don't have to do this work, because for odd roots, you can take the cube root of a negative number. So for example, cube root of -1 is -1. So we don't have the same restrictions when we have odd roots. So for every odd indexed root, you're going to have a domain of negative infinity to infinity. The next example says, use the graph of y equals f of x to answer the following question. What is the y-intercept of f? What are the x-intercepts of f? So I want to make sure we know what a y-intercept is. A y-intercept is where the graph crosses the y-axis. So let's go look at this picture. Our y-axis is this vertical axis. And I notice that the graph crosses through the y-axis at this location right here. And if we read that location, it's 0, 0. So we have a y-intercept of 0. Then we want to answer the other part, which is what are the x-intercepts? An x-intercept is where the graph crosses the x-axis. So the x-axis is this horizontal axis here. And I notice that the graph, if I follow the graph, it crosses that x-axis here at negative 3.4. The graph then crosses the x-axis again here at 0, 0. And it crosses again at 9, 0. And if we continue on, even though we have this dot here, this dot is drawn as open, so that's not part of the graph. So we do have three x-intercepts of negative 3.4, 0, and 9. Negative 3.4, 0, and 9 would be those x-intercepts. So the next example I have here says use the graph to determine the domain and range of the function. So remember, the domain is the set of all first coordinates and the range is the set of all second coordinates. So the strategy that I like to use to find the domain of the function when you have a graph is to hold my pencil vertically. I'm going to hold the pencil vertically and sweep from left to right. Left to right takes you from smallest to largest. So if I hold that pencil from left to right, I want to think about when is the first time that I hit the graph. So for this one, the first time I hit the graph would be just after I get to this negative 8 here. So my domain is going to start at that negative 8. And as I go from left to right, I'm trying to think when is the last time I hit the graph. The last time I hit the graph will be at this 5. Now you'll notice that I'm going to put a parenthesis on the negative 8. That's because that's an open circle. And a bracket on the 5 because that is a closed circle at that point. So that's how I find the domain. Then the range is all the second coordinates or the y values. So I'm going to hold my pencil horizontally instead of vertically and go from bottom to top. So if I hold it horizontally and go from bottom to top, the first time I hit the graph is when I get to this y equals negative 10. Then keep going. The last time I hit the graph going vertically from bottom to top is at this y of 6. I'm going to put a bracket on the 6 and a parenthesis on the negative 10, and that's because we have an open circle on this one and a closed circle on this one.